Okay, stats. So I'm actually in my classroom, which means that the noise level should be very good this time. Hopefully you can hear me very clearly and there won't be any background noise. So, section 5 is going to be the only section we cover this week, and it's going to be your goal to try to make yourself as much of an expert on it as possible. So this section is on paired comparisons. Now, if that looks familiar to you, it's because we've done paired comparisons before, but it was way, way back when we first talked about correlation. One of the things we learned is that because there's so much variability just from person to person or item to item that you might be testing on, that it's a good idea sometimes to come up with ways to isolate those variables and try to remove them before proceeding. In paired comparisons, what we try to do is one of two things. Either we try to pair a person or an object up with something that has similar characteristics, or in the most ideal situation, we give all of the treatments to both subjects. So it's one of those things where the second method is definitely the best, but it's going to require more resources and, of course, more time. So when exactly should we be using a paired comparison? If you think back to the conditions in 9.4, if I wanted to compare two means that came from two samples, one of the things that I had to check when I would go with my conditions in the first bullet point was that not only did I have random samples, but also those samples had to be independent of each other. What happens if they're not independent of each other? Does that mean that I immediately can no longer do any sort of analysis? Well, no. It just means that I have to probably do some sort of paired comparison. So realistically, these are used when you have one larger sample of data that can be combined into one overall difference. So we're going to be taking the differences. Now there's an activity that talks about measuring a hand, but I want to go to something we should already be familiar with, and that was the heart rate. We looked way back at seeing how people's heart rates fluctuate just from person to person, and then their goal was to determine if sitting and standing affected the heart rate in any sort of significant fashion. Under a completely random design, if, in fact, there were no external variables to worry about, I could randomly assign one group of people to sit, one group of people to stand. I could take their heart rates and see if there was a difference. That unfortunately doesn't take into account the overall difference that person to person has when it comes to their own heart rate. So maybe what I do first is try to get everybody's resting heart rate. And then after I get that resting heart rate, I pair them up with somebody who has a similar resting heart rate to them. That would be called a matched pairs design. You can see that half of the units were assigned to sit, the other half were assigned to stand, and unlike the completely random design, you will see that there's not as much fluctuation from person to person. But because I'm pairing them up, it's no longer necessarily as meaningful to do a direct comparison from one group to the other, and instead it makes a lot more sense to just look at the overall difference between standing and sitting. Because in that situation, I feel comfortable saying that that variable that I was worried about has been eliminated. That's why I paired people who had similar resting heart rates. Now that data you can see still has some pretty wild fluctuations. We had a result of negative 24. We also had a result of positive 30, which still gives us a large range of values. Now what would be better is, of course, have every person both sit and stand. Because then I'm not just getting you with a similar person, I'm getting you with the same person, and that person is yourself. I have you sit, take your resting heart rate. I have you stand, take your resting heart rate, and then I compare them. You will see that yes, we have twice as much data because we had to perform the task twice instead of splitting the groups up in half and half. That in and of itself is a benefit, having more data. You will see that I still took the differences, But notice that the range of differences is now much, much smaller. In fact, looking at the range of differences, there are no negative values whatsoever. And instead, all of the values are positive, with the maximum value being 20. That is much more consistent data, and more than likely, more reliable. So down below are the summary statistics for each. You can look at those summary statistics, and you could try to run an analysis on these using, either in the case of a completely random design, you could try a 2-sample test, or in the case of the matched pairs design or the repeated measure design, we can use what's going to be known as a paired observation test. So if you have 2 independent samples, you're using a completely random design. This is literally them repeating information from section 9.4. They're running it just like they would from 9.4. There is nothing new here. When they do their analysis, they eventually get to the point where you can see that the confidence interval that they calculated ran from negative 8.96 to positive 14.67. Clearly, 0 is in that confidence interval, and so they couldn't come to any statistically significant conclusion. When they ran a matched pairs design, they got some more consistent data. You can see that the summary statistics are given, but rather than us list them as x bar sub 1 and x bar sub 2, we're going to list it as d bar, which is just the average of the differences, okay? So d bar is typically the notation we will use when we assume that data really wasn't independent and should have been combined. You will see for standard deviation, they use S sub d. So they once again ran a confidence interval, and you can see that the numbers are quite a bit different. This time we have negative 3.44 to positive 10.86. The big difference here between the last one and this one is that the range of values has decreased immensely. We have way, way, way more precision now. However, the result has not changed. Since 0 is in the confidence interval, there is still nothing statistically significant about this result. But what about the best method, the repeated measure? If time and money are not a problem, repeated measure is always going to be more precise than an actual matched pairs design. That doesn't mean that a matched pairs design can't be extremely accurate. It just means it won't be as accurate as a repeated measure. So if I'm still convinced that standing is a factor that increases heart rate over sitting, the only way for me to really definitively get that result is through repeated measure. I could have hoped to have proven it with matched pairs, but I didn't. And more than likely, if somebody were to repeat that test numerous times, they would only be getting statistically significant results by error. But with a repeated measure design, especially if it's a large enough sample size, they should get those results very, very quickly. So you will see that this looks very similar in terms of its calculation to the matched pairs. They're still using d bar to represent the average difference, and they're proceeding as such. Finally, they get a confidence interval that run from 6.31, that's positive, to 10.41. We've now finally gotten a confidence interval that does not contain the number 0. And because it doesn't, we've finally been able to reach a conclusion that it is statistically significant. Now, Donald always liked to use the phrase gerrymandering statistics, and if somebody wanted to prove something, you could possibly say, well, maybe they just kept doing a different test until they eventually got the result they got. I would agree with you, except for the fact that the repeated measure, by all of its kind of setup, is the most accurate test of the 3. So if the repeated measure test says something that the other tests don't, you're more likely to rely on that repeated measure test. If one of the other tests had become statistically significant and then the repeated measure test said that it wasn't statistically significant, you're still going to rely on that repeated measure test. So when we go to check the conditions for paired observations, we still have to check normality, but there's a big difference when checking normality. Instead of checking to see if both samples are normal, you're actually going to take the differences between them, and then you're going to check if that difference is normal. So you will see that when they did a matched pairs, they actually got a really, really symmetrical distribution. But then on the repeated measure, it's not quite as symmetrical. But the key here is that in the repeated measure, the top one, it's way more precise. Look at those differences. They range from just over 0 to just under 20. With the matched pairs, they range from negative 25-ish all the way up to positive 30. Being normal is good, and it actually tells you that both of these tests were valid. The reason, though, that the repeated measure gave us a different result from the matched pairs is we were able to dial in the precision. Keep in mind that even on the matched pairs, we had an interval that ranged from a decently small negative value to a decently large positive value, but the real result could have been anywhere between those two numbers. And the repeated measure allows us to really dial in on where the true value is, which the matched pairs won't. So that's why, even though the matched pairs looks like it's better in terms of normality, both of these tests were completely valid based on what I'm looking at. So you will see that the book likes to call this a confidence interval for the mean difference from a paired observation. Now, last section, we were doing a confidence interval for the difference of two means. I hate calling one the mean of a difference and the other one the difference of two means. I think that can be very confusing. So I would like you to just simply call the ones that we use in this section a confidence interval for a paired observation and a significance test for a paired observation. If you do that, I don't think you'll mix it up with the ones from 9.4. So what are the conditions that you must check? In the case of a survey, you have to have a random sample from one, and this is key, one population, okay? So this is one large population of data, all right? It says in the case of an experiment, the treatments must have been randomly assigned within each pair. If the same subject is assigned both treatments, the treatments must have been assigned in random order. So in the case of a repeated measure, you're still supposed to randomly assign the order. That's where the randomness comes in there. But you're no longer checking for independence because you're doing a paired observation because the results were specifically not independent. Normality. You are checking that the differences between the data are actually normal. Not that each separate sample is normal, that the differences are normal. And then finally, same with the sample size as last section. If it's a survey, the size of the population should be 10 times larger than the sample. For notation, we like to use D rather than X bar. Okay, so we'll be using D bar to represent the average difference. And when you give your interpretation, you're going to say something along the lines of, I'm 95% confident that the mean of the difference, so mean of the difference, not the difference between the means, okay? So that the mean of the difference is somewhere between blank and blank, okay? Okay, so now what happens if you want to run a significance test? So when you want to run a significance test, you're still going to start off by 1, checking the conditions, and then 2, stating your hypotheses. The null hypothesis is almost always just going to be written as mu sub d equals 0. Now, I notice that they put the versus mu sub d greater than 0, but realistically here, that could be a not equal to or a less than. They're being very specific to this problem, okay? So the null hypothesis, mu sub d equals 0. The alternative hypothesis, either not equal to, greater than, or less than. But here comes the big difference. On the calculator, even though we started off with 2 samples, you will not be using the 2 sample when you are doing it on the calculator. What you're going to be using apologize. I thought I already had this pulled up. Which sadly I do not. All right. So what you're going to be pulling up on your calculator is, after going to Stat, and going over to the test menu, you're going to actually just pick option number 2, the t-test, or option number 8, the t-interval. Because what's going to happen, let's say we're pretending here for a minute, is if I go into my lists and I take some data that's in L1 and L2, I would have to pretend here to put some numbers in. And I'm just putting wildly crazy numbers in here so that we get some interesting results. I know that more than likely this is going to fail the normal check, but that's okay. All right, so I've put in kind of crazy numbers there. What you're going to do is you're going to come over here, and I would use L3, and you're going to take the difference. Now, if the numbers in one set are typically larger than the numbers in the other, you might want to always just choose larger numbers minus smaller numbers. But a lot of times they're going to tell you which values to take the difference for, or it's going to be kind of straightforward. If I'm testing a medication versus a control, I definitely want to see if the medication's result minus the control's result gives me a specific value. So I don't know if this is going to work or not, but let's just pretend I take L1 minus L2. And you can see, actually, it looks like it's a 50-50 split. I had 3 positive numbers and 3 negative numbers. So I don't think it really mattered if I did 1 minus 2 or if I had done 2 minus 1. But that's where telling me what mu sub d stands for will be really important. When you state your null hypothesis, you're going to put that mu sub d equals 0, where mu sub d is the difference between blank and blank. And you'll have to tell me, was that the difference between standing and sitting and checking your heart rate? Or maybe mu sub d was the difference between sitting and standing when checking your heart rate. You can see that the order in which you make your statement will matter. So when I go to check normality, I'm not checking L1. No, I'm not checking L2. I'm going to go into my stat plot, and I'm actually going to be checking L3. So for my X list, I want it to say L3. And for my Y list, I just want it to say 1 because it's just that single list of values. And I don't know why it tried to enter, because I didn't try to actually enter it. But, oh shoot, I see what the problem is. I did not highlight the box and whisker plot. And that's obviously going to be a problem. So let's try that again. So I have the data. Oh, I didn't want to run a test yet. We were checking normality. I'm sorry, I'm getting all ahead of myself. Okay, so let me come down here. Let me highlight the box and whisker plot. There we go. L3 has the differences in it. The frequencies are 1. And now I'll hit zoom 9. And again, because I made these numbers up, it won't surprise me if this is kind of crazy. However, look at that. Me just kind of arbitrarily typing in numbers has led to what appears to be a nearly perfectly symmetrical box and whisker plot. Now, if it's not perfectly symmetrical, you should technically use the 1540 guideline, but just like in section 9.4, the 1540 guideline is very, very conservative. Honestly, you can get away with samples of about 30, even if it's not very normal. And if your sample is around, I'd say probably 10, as long as there's no extreme skewness or outliers, you can also still get away with performing the test. The fact that you're combining data is what allows you to kind of get away with that slightly less specific outcome. So even though 1540 is a guideline, you can typically dial both of those numbers down a little bit. So anyway, this would have been a perfect one for me to run a significance test on. So now I could perform my test. I'd go over to test. And like I said, even though I had two pieces of information, remember I put data in L1, I put data in L2, I'm actually only going to be testing the differences. So I'll come down here to t-test. Now, because the null hypothesis would be that the differences are 0, here's the good news for you. The null mu is actually your mu sub d. You're always going to put 0 here. So you don't have to worry about changing this number. 0 is what you're assuming it is, meaning that there's no difference between the two. And the alternative is usually either not equal to or greater than. But of course, that depends on which one you assign to your first value and which one you do assign to your second value, and you'll state that accordingly. So obviously I want L3 here because that's where my differences are located, and I'll just run a test on something that would be not equal to. So again, these are all made up pretend numbers. I just want to show you that if I leave it as 0, I plug in my values, I press enter, it's going to give me a test statistic. It's going to give me a p-value, and because I made up these numbers, they ended up actually balancing themselves out really, really well. So I end up with a p-value of 0.952, which pretty much said that my numbers were completely and totally random. If I would have got a statistically significant result on this set of numbers I just made up, that means that by accident, I would have been typing in numbers that were not random. So kind of interesting to see just how random my numbers were. So anyway, guys, that is how you will insert the data. It might look like two samples, but because they are not independent of each other, you want to combine their results to create a difference. That difference that you're combining is going to end up giving you a single sample, and that is the sample that you're going to run all of your data on. Okay?